inside look into these efforts, how to architect Kubernetes for GPUs and for extreme scale. My first touch point with a Neocloud was actually in August 2020 when the CoreWeave founders reached out to us. We were building the vCluster open source project, and these guys hit us up and said, hey, we're building this GPU cloud. We're effectively building an AWS competitor, but with GPUs, and we'd love to do it with vCluster. We're very Kubernetes native, and we want to build it on top of vCluster. This was August 2020. Just for reference, to show you how early this was, ChatGPT was announced in November 22. So this was a lot long ago, very, very long ago, much earlier than ChatGPT even. And this company grew incredibly fast. CoreWeave is the first iconic AI cloud that has been purpose-built for AI workloads. And they went public last year. So very, very quick trajectory within 5 years from pretty much nowhere, right? They were a team of 20 people or so when we met them to IPO. And they're powering some of the largest GPU clusters in the world today. Why do AI clouds like CoreWeave care about Kubernetes? Why did they reach out to us in the first place? It's because Kubernetes becomes effectively an offering that turns your GPU capacity, it turns you from a capacity provider into an actual cloud offering. If you just have inventory of GPUs, you're pretty much just a data center, but not a cloud offering. So we need this fundamental platform layer. And why do we need it? Because AI training needs clusters, AI training needs scheduling. Those are terms that are very, very familiar in Kubernetes land. So inherently, when you look at a lot of OpenAI's tech block in the early days, it was a lot about Kubernetes. If you're reading up on inference today, it's predominantly about Kubernetes. And this hyperscaler-like experience is really what a lot of folks expect, right? You want to consume GPUs. You can obviously rent bare metal racks from a capacity provider, but the experience that most of us are familiar with is the AWS-like experience, where you just sign up, spin up a cluster, auto-scale the cluster, self-service, right? And CoreWeave wanted to build that. They wanted to be an actual cloud rather than just a capacity provider. An additional benefit for them is portability and familiarity for their customers. So moving workloads from an AWS over to now the new land of GPU clouds is much easier if you're providing an interface that people are familiar with. So if you are providing a managed Kubernetes offering, then of course people are familiar with EKS, GKE, AKS, etc. And it makes the migration easier, but it also allows your end customers, if you have a stable Kubernetes offering, to immediately deploy additional platform services on top. Think of your observability stack, think about security tools, right? Just look at Artifact Hub and all the Helm charts that Kubernetes offers out of the box. That's a really great benefit for most companies to not just start with something entirely new, but start with something familiar. And then last but not least, and this is often a very hidden part, is cloud operations require a lot of reconciliation, and we're all probably very familiar with reconciliation loops in Kubernetes in particular. That comes in very, very handy when you're building infrastructure where GPUs fail, networks need to be reconfigured, nodes need to be drained and rejoined. All of this sounds really, really familiar in Kubernetes land. So building on top of Kubernetes also for your internal tooling as an AI cloud provider is really, really helpful. And when you look at CoreWeave, for example, everything under the hood is Kubernetes. And you can listen, this is no secret sauce, you can listen to any of their public talks. They're very, very open about how they're building their platform in a very, very cloud native way. What is the difference between a regular, Kubernetes cluster, upstream Kubernetes, and EKS though? It's quite challenging for someone to build EKS. Because if you take, this is just a very trivial example. If you take vanilla upstream Kubernetes, and maybe you do Kelsey Hightower's the hard way guide, and you spin up Kubernetes, then you'll find that if you run kubectl get nodes, for example, you see the control plane nodes. If you run kubectl get pods, you see all kinds of services in that cluster. If you spin up an EKS cluster, it looks quite different. You don't see the control plane nodes. That is outside of your purview. It is managed by the cloud provider. So if you are CoreWeave, you have to build this experience that looks much more like this. When I run kubectl get nodes, I only see my worker nodes. I don't have access to the control plane nodes. They are off limits for me because CoreWeave guarantees the uptime for that control plane, just like AWS does. So quite challenging. Those were some of the challenges that CoreWeave saw when they reached out to us in the early days. But vCluster in 2020 is not vCluster of today. So let me recap what vCluster is, so all of you understand what CoreWeave was seeking out when they reached out to us. The standard Kubernetes, we're all familiar with this. You have a couple of namespaces, you have nodes, you have a shared cluster, you have a control plane. That is how standard Kubernetes looks like. And in a bunch of enterprises, they effectively segregate projects or teams by namespaces. That is not really the AWS EKS experience that CoreWeave was trying to build. So they looked at alternatives. What vCluster was in 2020 is effectively what you're seeing on the right-hand side over here. So it's still a shared cluster. We call that host cluster. But instead of giving tenants direct access to the API server that makes up that host cluster, to the controller manager, to the scheduler, etc., we are spinning up a separate control plane now as a container inside the namespace. And then we're exposing that control plane for the particular tenant. That means I have a shared host cluster that owns all the nodes. And then I have, maybe 10 vClusters running and their control plane. And that control plane is exposed via load balancer, ingress, you name it. And now each tenant has their own control plane, their own etcd, their own state. And then what happens under the hood is the workloads get actually placed on the nodes of the underlying cluster. So it's kind of like a little bit of a nesting doll, right? Cluster on top of a cluster. That's what CoreWeave was really interested in because they were operating entirely on bare metal. And when you're operating on bare metal, you don't just have an EC2 API where you can say, oh, spin me up all these nodes, right? Spin me up 3 VMs with CPUs and I can spawn a control plane. Now, join in a couple of GPU nodes. It's very, very complex. So they were looking to build large GPU clusters, and they were really good at doing that manually. And then effectively layering in this vCluster layer to give that more EKS style experience and abstracting that away for their customers. However, abstraction is very challenging when you're looking at GPU workloads, and CoreWeave found that out. We found that out as well at the time. That's why I'm saying this is vCluster 2020. CoreWeave built this initial offering called CoreWeave Classic on top of vCluster. That is not what runs what they call CKS, the CoreWeave Kubernetes service today. And that is because it's quite challenging with GPU workloads. You have direct hardware access. You need to be aware of the topology. There's a very, very high performant network underlying all of this, right? So the Kubernetes overlay network is actually much more of a bottleneck and a problem for GPU workloads. And then, you're trying to reduce overhead as much as possible. So the fewer abstractions, the better. Minimal abstraction really was, CoreWeave's principle, which is why they, started building bare metal Kubernetes. They were one of the first, massive services to offer bare metal Kubernetes on top of GPUs, and that gave them a unique edge. And that's why, OpenAI and Microsoft consumed so much of their GPU resources, because they had the performance that nobody had at the time and the reliability, on top of obviously the capacity. So, throughout this process of working with CoreWeave over a couple of years, we adjusted what vCluster is. vCluster still provides these virtualized control planes where you can run a control plane as a pod and effectively show 0 worker nodes, and a lot of services can run outside of the cluster rather than inside of the cluster, similar to how EKS probably builds their services internally. But we introduced a concept that we call private nodes. And that is actually just a fancy term for saying we allow nodes to be kubeadm joined into these control planes rather than reusing the nodes of the underlying cluster. So it feels much more like a traditional Kubernetes cluster in terms of the actual workloads, because the workloads get now scheduled on top of a node that is completely attached to just one tenant rather than shared across the tenants. That allows you to also be much more topology aware, right? So these are the real nodes. In this model, we're abstracting the nodes away, even to the extent that a lot of our CPU-based customers, they turn on a feature called pseudo nodes, which effectively, anonymize the nodes and really make them look completely different than what's available on on the underlying system. With this approach, we'll show you the real node. There's still options that we have where you can strip away certain node information and hide certain things away for the end customer. But effectively, you get the real node, and you're exposing that real node to the particular tenant. So before this change towards GPUs, we were focused on shared nodes. That means tenant pods get synced onto the host cluster, workloads see an abstracted node, hardware is hidden behind this syncing layer between the virtual and the underlying host Kubernetes cluster, and that's really great for traditional workloads. There's a lot of companies using that. It's folks like Deloitte. There's a pretty big case study in the AWS Tech blog about how they use us on top of EKS that just got published last month. There's a bunch of banks using us, including some of the biggest banks in the world. Adobe, Deloitte, and a bunch of others are using us at pretty massive scale. But again, when you're entering GPU world, you need something different, and that's private nodes. With private nodes, you get the raw bare metal nodes. Could also be VMs, but most of our customers are actually joining bare metal nodes into these clusters. The workloads run on the actual hardware. You can expose the actual network to them. You can segregate the actual network. So when you're thinking about InfiniBand, you can separate the InfiniBand with P keys, right? You can set VLANs and VXLANs for your different customers. So real low-level network rather than overlay network that we typically see in Kubernetes, because you have such high-performance workloads where these GPUs need to be interconnected. And you're still retaining the virtual control plane and effectively all the goodness of Kubernetes and everything we built prior. But the big downside, you can probably see that here in the last bullet point, is that you're creating very rigid clusters now, right? Your kubeadm joining those into your tenants, right? You have static network configuration. All of the problems we didn't have beforehand, all of the problems that CoreWeave didn't want to have, right? The original design they had was like, let's create one large cluster per data center. And that makes it really easy, right? A node falls over, we'll take it out of that cluster, we put it back in that cluster, the network is all flat, right? Now it becomes a lot more problematic, right? A node, needs to be moved into a service tenant, into a VLAN specifically for servicing. Then it needs to be moved into a different network again afterwards, after the node has been serviced. So there's a lot of complexity that goes way beyond just kubeadm join when you run this approach. So we had to fix this as well. Manual provisioning, even for if you're thinking beyond Neoclouds, beyond AI cloud providers, if you're thinking about enterprises, for example, it's even worse. Let's say you're an enterprise and you provision, GPU nodes in your private data center for your 5 business units. How do you divvy them up? Do you give 10 nodes over here and 20 nodes over there and it's completely static? That's probably not what you want to do with the most expensive resource that you can possibly own in a data center. You kind of want utilization to be maximized to the biggest extent possible, because some of your tenants, they might be underutilizing the infrastructure. Others, they might be at capacity limit, and they could do so much more if they had more capacity. So how do you balance that within an enterprise? And the same question, goes to a lot of Neoclouds as well. They're trying to maximize utilization across their customer base. And they're launching offerings such as serverless inference. And when you think about that, it's all about maximizing how many tokens can we produce with the same amount of GPUs. So what we built is effectively what AWS built for EKS, right? In AWS, you have EKS Auto Mode, where Carpenter is baked into the Kubernetes distribution and wired up to EC2, which is obviously much easier because you have a really solid EC2 API that AWS has been building for like 20 years, right? So we had to do this effectively for bare metal provisioning, which was quite a challenge. We had to tie into a lot of different systems, for example, Canonical's MAS, into OpenStack Ironic. NVIDIA has their own provisioning system called BCM. There's a new one coming called Nico for DPUs. There's so much complexity on the bare metal provisioning layer that is obviously not something we wanted to be prescriptive on and tell our customers, hey, you need to use this specific system, right? Or you need to use our system, even worse. We needed to tie into all of these different APIs. So we decided to integrate Carpenter. Carpenter creates these node claims They can be created statically, by you just saying, like, let me resize this cluster from 3 to 7 nodes. Or they can be completely dynamically created based on the workloads that get scheduled inside the clusters, right? No matter how the node claims get created, the actual complex part is what happens in the bottom area here when the node claim needs to be fulfilled. So we now know Carpenter told us, hey, this node needs to be removed. That's relatively easy. We'll take it out, move it into a service tier. But what if a new node needs to be added? We have to know, the node pools. We have to know what nodes are available in which system. Then we have to go to the node provider, boot up a node, put it in the right Kubernetes cluster, tell the network automation tool to set the right network configuration. There's a lot of complexity under the hood that went into these systems. I wanted to show you one integration we built, purpose-built for GPU clouds. You might not be familiar with this company. They just raised their Series A. They're relatively small still, but they're growing really, really fast. It's called Netris. We have a deep partnership with them. They're effectively, one of the default solutions for network orchestration in a lot of the data centers that power AI workloads today. And what they essentially do is they abstract away, InfiniBand, Rocky, and all of these different protocols you have in a data center, and then they effectively say, okay, tenant A, tenant B, tenant C, and we can just tell them, hey, this node belongs to tenant A, B, or C, and they configure the underlying network correctly, literally like configuring the switches. Quite some complexity here going on in the data center. We had to build so much more beyond, just Kubernetes. It goes down all the way to the metal layer. We call this vMetal. This is all the integrations into the underlying system. Then vCluster, I showed you earlier, was quite expanded from what we originally launched in the vCluster open source project in 2021. And then we build a security layer on top as well, because if you're running, workloads on bare metal GPUs, you have a much bigger attack vector than if you're running in virtualized environments such as vSphere or EC2 VMs, etc. So how do you contain these workloads and make sure that faulty drivers and all of these issues don't spill over into the layers below? We build a technology that's similar to, for example, a gvisor. It's called vNode, and it's optimized specifically for bare metal workloads. Something very, very interesting, some private beta right now, relatively new. And then the latest thing we've been starting to work on when you're thinking about, AI clouds becoming actual cloud providers, Kubernetes is the starting point for most of them. But then, you look at AWS and the catalog of services, there's like 3,000 of them or something like that, right? It's also about managed databases, platforms, ML tooling, right? How can you provision all of this on top? And we call that certified stacks, which effectively helps, AI clouds, but also enterprises to spin up managed services on top of Kubernetes much, much faster and optimize them really for AI workloads. If you're interested in learning more what we're doing directly with NVIDIA, we have a reference architecture with them out there. It's a pretty in-depth technical documentation. It's about 50 pages or so. Really goes into the details of how to provision these systems on the GPU layer. I put the QR code here at the bottom if you want to have a closer read at this. Another thing I wanted to highlight is the ecosystem is quite different here. The traditional, gardeners and foresters of the world that we would typically look at in terms of recommendations, who's the leader in the Magic Quadrant, right? I'm sure we're all familiar with all of these topics. In AI land, one of the learnings for me was semi-analysis is kind of the kingmaker. They're effectively a very, very small research firm that is specialized on, semiconductor industry and everybody building on top of these accelerated chips. They have a ranking called ClusterMax. I would recommend anybody who is looking into GPUs to check that out. They have a very, very detailed read on each one of these cloud providers. They actually, were as friendly to point out that CoreWeave Classic wasn't secure enough running with vCluster, and that's why they had to change it to the new model to join in dedicated nodes and not using shared nodes. So they gave us a little bit of a diss in their previous cluster mix at some point, but I think we've made some improvements since then. For us, this is really a roadmap. They have different categories in different criteria that they're evaluating these AI clouds with. And we're effectively, taking this apart and trying to support them in as many of these criteria as possible. There's obviously some criteria we'll never be able to help them with. For example, HIPAA compliance, GDPR, right? Like those are things that these companies have to figure out without us. There might be other consultants that can help there. But for 87 out of the 142, checkbox criteria, specifically regarding security, lifecycle management, orchestration, you can imagine, but also tying into storage and networking and reliability of these systems, we're really hands-on helping these folks, build out, hyperscaler-like experiences, but on top of bare metal GPUs. vCluster has been working since the experience of CoreWeave with some of the leading cloud providers, including a bunch of them here in Europe. Nebius, to be named as one of the leading providers in Europe that's growing very, very fast. Polarize is actually a German provider that we work really, really closely with, building a data center here in Munich, I believe, and a couple more in the Nordics. Very, very interesting provider. And one of the things that I'm most excited about is not just AI clouds, there's also other use cases emerging. So managed Kubernetes for AI clouds was really the table stakes thing that a lot of folks have to figure out, either internally or as a public cloud provider. But we're now seeing sovereign clouds emerge with specific requirements towards data sovereignty. Then we're seeing enterprise AI factories being built, where the enterprise is starting to buy GPUs and put them in their private data centers. That's very, very exciting for us, and kind of bridging the gap between, our traditional business work and technology that we're focused on in the public cloud, now emerging in the private cloud specifically for GPUs for some of these enterprises. And then distributed inference, that's the last use case I wanted to show you real quick. Distributed inference is something really exciting. So when you're hearing the term token factory instead of AI factory, that's what a lot of people refer to. If you're chatting with ChatGPT or with Claude, that's effectively inference. You've probably seen there's a bunch of open source models out there. How do you leverage these open source models? Well, large-scale distributed inference providers help you do that. They help you fine-tune and train these models specifically for your use cases. They help you run open source models in different geos. Just kind of think like a CDN, right? A content delivery network, but instead of delivering content, you're delivering tokens to folks, using your particular use case with that particular model. One of the really interesting things we started to build is somewhat of a capacity aggregator, where you effectively tie in capacity from public clouds, Neoclouds, as well as your private cloud estate, which might be something like a DGX SuperPOD or similar systems, and then aggregate that into one API to run inference against, because inference is inherently distributed. If you're thinking about this use case, right, it's people interacting with models and people in a particular geo, and when they have a request against the model, right, latency matters. If you have everything in one data center in US East region, right, it doesn't really help you as much if you're in Asia or if you're in Europe. You want the latency to be much, much smaller, which is why a lot of traditional telcos are starting to enter this space and putting GPUs in their edge locations, for example. And now you suddenly have a Kubernetes fleet management problem, right? Where you have thousands of small Kubernetes clusters aggregating capacity up. And then you have locations that might go offline due to a power outage, right? There's a lot of complexity going on when you're using an offering such as Nebius Token Factory or Base 10 or any of these other inference offerings. A very interesting technology that we started leveraging here under the hood, to get a little bit more technical again, is Tailscale. We started integrating the open source Tailscale into vCluster, where we literally secure the connectivity between vCluster control plane as well as any of the nodes, as well as the traffic across the different nodes, with effectively a tailnet. So each one of these vClusters now has its own tailnet, and then the vCluster control plane connecting to the vCluster platform, which is the central aggregation and fleet management tool, is also in a separate tailnet. And that means connectivity can now happen across the wire. We've even seen people put the control planes in AWS, but then join in bare metal nodes from edge locations or from data centers that they're running, because they're effectively using the stability of an AWS in order to run the control plane, so they don't have to worry about that, and then they just have to worry about the reliability of the actual GPU nodes. So very, very interesting setup that powers some of the largest token factories out there that you might have already used in the past. To wrap up, I put 6 very, very interesting learnings for me as a traditional Kubernetes engineer venturing into AI infra here, that I want to share with all of you. The first one is, when people talk about multi-tenancy, they're not talking about Kubernetes multi-tenancy in this space. That was a big learning for us in the early days. Sometimes they tell us, the most important thing for us is multi-tenancy. And we're like, oh, interesting. Didn't you hear CoreWeave kind of went away from that approach and built single tenant clusters effectively, that they don't want to share nodes. And then for them, multi-tenancy means the data center is multi-tenant. So effectively, we're not building a data center just for Azure, right? That is the single tenant data center. Multi-tenant means we have 80 different labs and other customers in that data center, and we're dividing up by rack or by individual server. That was an interesting learning for us in the early days. The other one, I'm sure there's folks that have explored, vGPU, MIG, etc., ways to, slice up a GPU. Is pretty irrelevant for most of the large-scale use cases we've seen out there. I would probably say 90+% of the GPUs out there are not using any of this. Most of the use cases are large training, where you effectively need as many raw GPUs as possible and aggregating them up, or inference, where you have a similar problem. We haven't really seen a lot of demand for this. In the early days, we started investigating, researching, and building a lot in that direction. And then we found the real-world use cases are super small. The other one, I talked a lot about networking earlier. Tenant isolation doesn't just mean separate nodes, it means entirely separate physical networks. And overlay networking, like we're used to in terms of network policies, right? Things like OVN, etc., don't usually make the cut for most of these providers. It has to be strict isolation directly on the physical network. That was surprising for me as well, that it goes so deep in terms of isolation that everything else is not really an option. Number 4, and we probably all hate this one, old school manual sysadmin is prevailing. So you'd be surprised when you're seeing some of these, even if you're using some of these GPU clouds today and you're using their token factories. I've seen everything under the hood from some of the biggest providers out there. You won't believe how manual these clusters are set up, and how fragile all of those systems are. All of us here who have extensively worked in the public cloud and traditional private cloud have a much different standard in terms of automation and resilience than most AI workloads in AI companies do. Number 5 is everything breaks all the time, which probably is related to number 4, but it's also very much related to the fact that GPUs fail at a much higher rate. The complexity is much higher. The power consumption is much higher. And overall, these systems are, enormously large and complex, right? The networking is really complex. Some of these, when you just think about the power, some of these retrofitted data centers are, giant buildings, and then you have a tiny little rack in the middle, because that's all the power they have in that particular data center. But it's still, $1 billion of hardware running in that facility. It's kind of crazy. And number 6, I was talking about CoreWeave speed to market earlier. Speed is everything in this market. I think we've all seen how AI is, making its way into all of our lives, and how this space is evolving so quickly, how much capacity is coming online, and how it's still so constrained, right? Everybody's, seeing obviously these stock prices rise, and the demand for, memory. Hopefully all of you built your, home lab computers and whatever before the big memory crunch. Otherwise, things get a lot more expensive these days. And that comes from the demand being so high and far outpacing the supply. So people are catching up to really fill the supply, and speed is everything in this market. That's the end of the talk. Hopefully this was an interesting insight into AI clouds and AI factories, and even some token factory knowledge that we've gained over the past 5 years being in this space. I'm going to be at Raise with my team in Paris, I think next week. If anybody's there, definitely come by. We have a booth there. Otherwise, I'm here today and tomorrow. Happy to chat about anything. Here's my LinkedIn if you want to connect. And yeah, happy to hear your experiences with GPUs, and anybody who has seen similar topics and wants to partner, exchange notes. I'll be around for the next 2 days. Thank you.